The aluminum mesh that we're testing in this project could be used to protect personnel, vehicles, or structures for the military. In other words, it could save lives.
The objective of the project is to characterize the aluminum mesh. We want to find out how good this mesh is at protecting objects from blast waves. The key parts of the testing program are threefold: modeling of the aluminum mesh, testing in the arena test format, which is a small charge, and testing in the shock tube, which replicates a larger blast. The modeling software that we have chosen for the modeling of this aluminum mesh is called AUTODYN. Using a function of porosity, we can actually replicate the arena test and the shock tube test fairly closely.
This is an example of a model we did for the arena testing. We did it in 2D symmetry, so as you can see here, we have a very small charge, and this is 10 layers of aluminum mesh, and this is the 20 layers. As the wave gets closer to the mesh and then it starts hitting the mesh, you see in this yellow here and some of this yellow here, some of the peak pressure getting mitigated by the mesh. You can see large pressure where there was no mesh, and then back here around it, pressure is not as high. Without any mesh, we're getting almost 200 kilopascals with atmospheric pressure after you subtract it, so around 90 or 95. And with 10 layers, we're looking around 75 or so. And then with 20 layers, we're looking at about 60. It does, in fact, take peak off that pressure wave.
The facility in Georgetown is located in an underground quarry. And this is an area where our shock tube and arena tests are located. We are on the second level, which is around 250 feet underground. Final excavation ends up being about 60 feet tall and 35 to 40 feet wide. The explosive product that we use in Georgetown is a desensitized RDX bulk product. What that means is we get to weigh the charges individually. And I use a gram scale that is accurate to at least 1/10 of a gram. What we do is weigh the charges out, and we actually place those charges in either a plastic bag or a latex glove that we might be wearing while we're assembling the charges. The placement of the detonator within the explosive charge is very important. What you want to do is make sure that the end of the detonator is as close to the center of the charge as possible. In the arena test, we're using small amounts of explosives and using scale distance formulas to determine what distances we want to put the aluminum mesh away from the explosive charge. In the arena test, we have a small explosive charge and aluminum mesh around 3 sides. We leave the 4th side blank because we take a pressure at the same distance as the other 3 pressure sensors behind the mesh to determine if there is a reduction in pressure.
Fire in the hole! Fire in the hole! Fire in the hole!
3, 2, 1. When an explosive detonates, what happens is the pressure radiates in 3 dimensions as a sphere. If you put your pressure sensors at equal distances from the center of the explosion, you should get the same pressure. The only variable we're changing is we're putting different layers of mesh between the explosive and 3 of our 4 pressure sensors. The shock tube tests were designed in order to provide a longer wavelength on a pressure wave. And what we have done is replicate a 500 kilogram and a 1,000 kilogram bomb with this shock tube. To describe it, it's 120 feet long. The inside dimensions are 8.5 feet by 8.5 feet. It's basically a steel box.
What we got a picture of here is the shock tube. Darker boxes inside are the actual shipping containers that are used for the shock tube. You can see the charge here. It's already detonated. It's almost to the edge of the tube. And all of these red dots are the sensors that will measure pressure. We have 52 gauges on that plate, but just to give you an example, I'll pick around 5. Atmospheric pressure is around 101 kilopascals, and it rises up in exponential decay like a shock wave should.
In the shock tube, we have used charges ranging from 40 grams to about 900 grams, and that's pretty much the operating limit of the shock tube that we've developed. At the end of this shock tube, we have a plate with aperture holes in it so we can place different layers of mesh on those plates and again test the reduction in pressure. What happens is when you detonate this explosive in the shock tube, the energy is not allowed to expand in 3 dimensions, but forced down the tunnel. When you put the sensors on the back of the mesh, it tells you whether you get a reduction or not. Some of the tools that we use for blast mitigation testing are very important. The data trap is our data acquisition system that records at up to 10 megahertz, which means that it takes 10 million measurements per second. Now this is important because you don't want to miss any of the peaks in your pressure wave. We use that data trap in conjunction with piezoelectric sensors and cables to collect the pressure data from the blast. This project potentially has great benefit to the military. I think they're always looking for blast-resistant products to protect the soldiers. One of the main advantages that you have with this product is it's very lightweight, which means that it could be applied to almost any vehicle with limited retrofit. You don't have to add power or anything to this equipment to make it still useful. I think with the data that we've collected and the modeling that we've done, we've shown that it does have potential for reducing blast pressures on whatever you want to protect. If testing is continued and we validate this completely as a viable product for blast protection, I can see the military using this in a lot of different applications. And hopefully, within the near future, we can really get this field ready and able to use by the soldiers.
IEDs are probably the most deadly threat, in my opinion, in theater right now, especially for the people out running the roads. Coming out here and being part of a mission like this and seeing how we can mitigate the blast effects on different vehicles and using different materials, it means a lot to me because it's saving my soldiers' lives. IEDs are very prevalent and dangerous for us right now. That is a weapon that is convenient for them because they can place it and leave and not have to worry about who it hits or how it hits or anything else. A lot of times they're placed and it's what they call victim initiated, where they put out a pressure wire and we run over it, so we initiate our own devices. Yeah. So
Stick 2 in there?
Yeah.
Yeah, I'm gonna stand at this side of the road. It's all clear.
Really, the whole idea that I wanted to get out here is, okay, if this stuff prevents pressure of the blast coming to the vehicle, how are we going to apply it?
Right.
Because it's hard to work with the way it is, and we have to do something to make it easier to do. See on this vehicle test with no mesh, the floor pan's completely sunk, and the driver's compartment is pretty much destroyed. You can disregard the fire completely and just look at the blast effect itself. The seat's gone, and I mean it's just completely mangled and pretty much destroyed. On the other vehicle where we did have mesh applied, it's flat and the operator's compartment is pretty much intact. And I think really the only difference was that there was mesh underneath that vehicle. You can see on this one, the rear wheel was knocked off on this vehicle during the test, but the operator's compartment is still intact. The floor pan itself is relatively flat, and you can see that the blast effect was much less with the aluminum mesh, and it's actually still there. It's come loose a little bit, but the mesh itself is still applied to the bottom. I think it tells you something about the performance of the mesh. Test results to date are quite astonishing to me. I find it very intriguing that with 20 layers of this mesh, you can get a 30% reduction in pressure. I thought in the initial phases of the project that perhaps we'd find out at the larger charges that we wouldn't get reduction, but in fact that's not the case. And even though with these shock tube tests we see that mesh just get blown out right through the sensors, it's amazing that we're still seeing a pressure reduction. It makes me believe that there could be an application for this product. I think it may be a little bit difficult to handle, but with more work and maybe combining it with some other materials, it could be a really viable solution for protection.